All right, good morning, or actually it looks like we have people from all around the world. So good morning, afternoon, or evening, whatever it might be. Yeah, today we're going to talk about resolution and bandwidth in servo control loops. And it's a classic trade-off. It's a classic switch that you can kind of play with in especially magnetic sensors, where you can kind of adjust an external filter and trade off lower bandwidth for higher resolution or lower resolution for higher dynamic bandwidth. So we will talk about magnetic angle sensing to start out with. It's got a lot of advantages in terms of cost, flexibility, and these days, as the resolution and bandwidth and INL gets better and better, it's becoming very, very popular for both brushless DC, stepper, all kinds of motor servo feedback. We'll talk about some of the systematic error sources that we see and some of the random error sources that we see in sensors, particularly magnetic sensors. We will then talk about how to understand what the real resolution is. How do we really define resolution? What does it actually mean? And then the flip side of that, of course, is the dynamic bandwidth. And so when you make a trade-off for higher resolution, what does that do? How does that actually affect your control system? And we'll finish off, like Kelly said, with a little bit of Q&A. So to jump right in, let's first take a look at the systematic error sources in a magnetic angle sensor. So integral nonlinearity is the first one. It's intrinsic to any sensor. You're going to have some INL, and there's a little chart over here where we show the difference between these types of errors and the difference between the kind of ideal waveform. So the ideal waveform, of course, if you're running a rotor at a consistent speed, is just to go a 0 to 360 straight line, and then it rolls over back to 0 and back to 360. I'm not sure, Kelly, I'll ask you, can you see my pin marker? It's not showing up on my second screen, my little laser pointer.
I am not seeing that. So if you want to try and adjust that.
Aha. How about
there
now?
We go. I now see it.
All right. Yep. I was using pin. Okay. So 0 to 360 straight line, 0 to 360 as it rolls over. And then what do we actually see? Well, because of integral nonlinearity, and let's forget about this lag right now, or actually we can cover it. Latency of a sensor causes angle lag. So latency would be the time difference from here to here, which causes an angle lag from here to here, if that makes sense. In other words, because of the time latency of a sensor's output, the real system has moved on. Since we're running at a consistent speed, the real system has moved on. And so there's an angle lag caused by the time latency. And so that's what this dotted line represents. But the dotted line is still nice and straight. It's 0 to 360, nice and straight, just shifted in time, or you could look at it as shifted in angle. INL is the greatest excursion from that straight, perfect line. And there's always an INL intrinsic to any sensor. So it could be on the order of a few degrees, or it could be on the order of, some tenths of a degree. The intrinsic INL is then further, let's say, complicated or further increased by any type of magnetic misalignment with the sensor. So we consider these two different things, but they both affect INL. This one is just the intrinsic INL of a sensor. This one is INL caused by magnetic misalignment. And sometimes that's correctable. Certainly all of this stuff is correctable with enough calibration, but without calibration, sometimes even this is correctable. So I kind of jumped ahead before to talk about latency, but let's then take a look at latency and how it actually affects things. So let's assume that we're running at 30,000 RPMs. It's a relatively quick motor. So 30,000 RPM, 0 to 360, 0 to 360. And if we've got a latency of 10 microseconds, that just directly translates into a 1.8 degree lag. So you have a 10 microsecond latency. That's a 1.8 degree lag. MPS does have a part that has latency compensation built in. And so it is effectively a 0 microsecond latency, which means that this dotted line is reshifted back to match the solid line, and it's a 0 microsecond latency, which means a 0 degree lag. Those are the systematic error sources. We'll take a look at another example. So if we had, again, we'll stack all these errors up now. So again, we'll talk about this 10 microsecond latency that causes a 1.8 degree lag. This actually, since we're in degrees, should be lag. I apologize for that error. But let's take an INL of, for instance, 1 degree, and then a magnetic misalignment, which causes a further INL of 0.3 degree. And then due to that 10 microsecond latency, a 1.8 degree lag that can stack up and cause up to a 3.1 degree error. We have some process in place where in the factory, we can actually calibrate our parts. And so you'll see more of an intrinsic 0.5 maximum over temperature. Magnetic is magnetic. The part's going to see what it sees. So we'll assume the same as any sensor. And then because of our latency compensation, a 0 degree latency. And so a total error of only 0.8 degrees. I mentioned you can further calibrate this stuff out if you take the time at manufacturing to run a couple loops of the motor. You could take this, the intrinsic INL can be calibrated. It's going to drift over temperature, so there's still going to be a remnant of around 0.1 degrees, unless you want to temperature compensate, which gets really complex. But I don't think you're going to get under 0.1 degrees, but you can completely calibrate out the magnetic misalignment, and with no latency, you could get down to a total error of on the order of 0.1 or possibly even less degrees. It's important to remember that latency can't be calibrated out because it's speed dependent. So unless you know what your speed is and you're depending on the sensor to know what your speed is, higher speed is going to cause a higher error. So that part, that can't be calibrated out. All right, we'll get back to a little bit more of this MA600 later on in the presentation, but let's move on to our random error sources. And random error sources is noise, right? Usually Gaussian, but we'll model everything as relatively Gaussian. We capture the impact of noise with our resolution spec. And so you can see here, we've captured it in these little kind of error bars, because at any given rotation, you might get an output that's anywhere across this error bar. It's a random thing, so it could fall anywhere in here. It's got a kind of a Gaussian distribution, so you expect it to fall in the middle, but could be anywhere within 3 standard deviations. We can reduce this noise by filtering, and we do on all of our position sensors. We have a back-end filter that is a sliding window filter that's essentially an averaging filter, and that reduces the noise. But you don't get that for free, like everything in engineering. You have to pay a price, and the price is the sensor dynamic bandwidth. That bandwidth impacts loop stability. If your bandwidth gets too low, you can actually cause your PID or your servo loop to go unstable. And even when it's not unstable, it still affects, we'll see on the next slide, it still affects kind of overshoot and how long it takes to come back to a steady state during accelerations and deceleration. So the important thing here is we have to consider both resolution and bandwidth. And that's obviously going to be really dependent on the exact type of control that you're trying to implement. If it's full FOC, if it's just a PI controller, or if it's more complex, more advanced with multiple nested loops. When the sensor bandwidth is too low, it looks like angle error. So we need to determine the real resolution of a sensor. And that we'll talk in depth about is how do we determine the actual resolution of a sensor. And then we need to understand the relationship between resolution and bandwidth. So let's take a look at a quick real example. So I've got a system here that is trying to track speed. So we're in speed control, and we're going to accelerate from 0 to 1,000 RPMs and then try to hold steady at 1,000 RPMs. The blue line is the line that we're trying to control to. When I set my cutoff frequency of the sensor to 310 Hertz, you can see that you get a significant lag behind, because during acceleration, by the way, I should mention that our window filter does have a speed state variable. So at constant speed, it doesn't have any error or any angle lag. It does not have an acceleration state variable. So this is where you'll see during acceleration is when we'll see this angle lag. So during the acceleration, we see a lag. We see an overshoot, and then it oscillates and comes back eventually down to its set point. And it takes on the order of 20 milliseconds at a relatively, this is not a super aggressive acceleration, but our cutoff frequency is 310 Hertz. Down here, if I up the cutoff frequency to 2.8 kilohertz, in other words, I'm going to reduce the filter window. I'll show you that later in the presentation. But if we up this to 2.8 kilohertz, you see that we still have this overshoot and undershoot, but it stabilizes much more quickly. And the speed actually catches itself up before we even get into steady state. So the speed catches itself up, which is why there's an overshoot, undershoot, and we're back to stable in about half the time. It took 20 milliseconds at 310 Hertz. It takes about 10 milliseconds at 2.8 kilohertz. But this is not free, like I said. Now we have only a 13.2 bit resolution compared to the nice 14.3 bit resolution that we had with our 310 Hertz. And this is just showing, once we do this and we keep the cutoff frequency at the same level, we keep the filter window at the same level, we stop the motor and we just measure. We take 1,000 measurements and just see what bins they fall into. Well, up here, you can see that it's only basically a 3-bit jitter. Whereas down here, 1, 2, 3, 4, 5, 6, 7, 8, 9-bit jitter. Because these are shaped, though, you can see. So you're nine LSBs here, 3 LSBs here. Actually, I'm sorry, not 9 LSBs. Log 2 of 9. So about 3 LSBs here and about 1 LSB here is going to be fluctuating. In any case, 14.3 bits, 13.2 bits, and that's the trade-off. In general, and this is kind of a rough estimate, you can get, every time you want to get an extra half bit, you're going to double your, you're going to have your cutoff frequency. So every half bit extra resolution halves your cutoff frequency. All right, so we've been talking about resolution and these jittery bits. What does it actually mean? What exactly is resolution? It's an easy number for people to just throw onto a data sheet and say, hey, our sensor has whatever, 10 bits of resolution, 14 bits of resolution, 16 bits of resolution. What does it really mean? One way that you could look at it is to say, okay, well, if it's a 16-bit word and I say that my sensor has 14 bits of resolution, that means I should have 2 noisy bits. My 2 LSBs should be noisy. It's a little more complex than that. So we got to get into some metrology here and talk about measurement error. So here is a value that we're going to be measuring. So this is the quantity that we're measuring on the horizontal x-axis, and we have some value. That's the real value. As we take measurements, and we haven't moved the true value, we're just taking multiple measurements with that true value remaining the same, we get some noise. This part, the difference between here and the mean, is our systematic error that we talked about, usually INL. But this spread, these various points, that's due to noise. That's our noise error. So systematic error is essentially bias, and our peak-to-peak noise is our random error. And because this usually follows a Gaussian curve, or at least we model it as a Gaussian curve, because a lot of smart people have already done all the mathematics for Gaussian distributions. We can provide a lot of statistics based on just standard deviation. So we're going to say that the peak noise distribution, the peak-to-peak noise distribution, so from the furthest noise that we see over here to the furthest noise we see over here, is a 6 sigma or 6 standard deviation distribution. And if we look at some real Gaussian noise generated by a random number generator, you can see that if we do our 6 sigma plus minus 3 sigmas, we capture 99.73% of that noise. And those, again, these are well-known statistics. So in other words, if we claim plus minus 3 sigma or a 6 sigma distribution, only 0.2%, only 0.27% of the data is outside of our range. So 6 sigma is generally considered a very safe estimate of the total distribution. All right. So what does that have to do with resolution? We are going to define resolution now to say that if I take a single measurement, I have 2 possible positions, and I'm going to take a single measurement, I should be able to answer the question, is this system at position 1 or position 2? And I should be correct 99.73% of the time. In this case, my 2 positions are less than my resolution. So there is a good chance that if I were to take a measurement, there's a really good chance that that measurement would end up somewhere in here. And if it is, I can't really say whether it's position 1 or position 2. There's a decent chance that it might fall, let's say, here. And then I can say, well, it's probably at position 1, probably not at position 2, but certainly I'm not going to be right 99.73% of the time. So we're now going to start widening these positions out. And again, I've still got position 2 minus position 1 less than my resolution. And you can see that a lot of the times if I take a measurement, it's going to fall somewhere in here. And yeah, it's probably position 2 right here, but certainly I can't guarantee it 99.73% of the time. If I'm way out here, I could say, oh yeah, that's definitely position 2, but I'm almost never going to get less than 0.27% of the time am I ever even going to get a data point out here. So we separate these things out until we get to a point where if I take a measurement, it's very unlikely now that I'm going to get a measurement point in here, whether I'm at position 1 or position 2. And it's quite likely that it'll be somewhere in here. And let's say I find a point here. Yeah, that's position 1. And I'm right 99.73% of the time, because it would be position 2 will only show a measurement point out here far less than 0.27% of the time. So a very kind of mathematically rigorous way of talking about something I think is fairly intuitive if you just look at how we spread these things out until we get to a point where the peak-to-peak noise is 6 sigma between position 1 and position 2. And I can continue to widen these out, and then I get greater than the resolution. But this area where I just get to 99.73%, that is my resolution. So position 1 and position 2 are right at the edge of what I can determine the correct position 99.73% of the time. When we start talking about an AD converter, and actually it's funny, MPS, our sensors don't contain an A to D converter because our front end is a little bit different. We have a time to digital converter. And if you ever, it's called spin axis. If you ever interested in looking up, I wrote an article about it some years ago. I think it was in Bodo's Power Magazine. But look up my name, Ted Smith, and spin axis if you want to understand how our front end works. But we still model it the same way as any competitor or anybody that uses an A to D converter because the model still stands. It fits. In an A to D converter, you have an actual resolution of the converter itself, and so that creates a measurement grid. Ideally, that grid has to be finer than the actual noise distribution of the sensor. If it's not, then your resolution is now defined by your A to D converter, which is bad. We want to make sure that we capture all the bins that the sensor noise could fall into. And so if we would like to say, all right, of this whole system, what is the resolution in bits? It is the log 2, because it's binary, so log base 2 of the full scale measurement, the maximum measurement that you can make, divided by the peak to peak noise. This is so-called noise-free code resolution for A to D converters, and it's equal to the number of stable bits. So again, here this shows this is goofy. It shows a 9-bit word. Normally you'll see an 8 or a 16, but whatever. A 9-bit word, and I've got 3 flickering bits. That means I've got at least a 6-bit resolution. And then because these flickering bits are flickering in a not completely random way, though it'll be a shaped way, it's going to be 6 point something bits of resolution. For an angle sensor, our full scale is 360 degrees, and we'll convert our noise into degrees essentially. So the sensor is going to output something like 0 to 65 535, or 0 to some however many bits it is. You can convert that into an angle, and we'll take our 6 sigma, so it's log 2 of 360 degrees divided by our 6 sigma angle. That's how we'll define resolution of an angle sensor. Okay, so for MPS, our MA702, this is an older part. Our MA702 has a 7.5-bit front end. Our time to digital converter has enough noise on it that the absolute output, resolution output, is 7.5 bits. We then have a filter, and again, it's that moving window filter that we'll talk about on the next slide. And the output then is actually 11.5 bits of resolution, because we're able to average a bunch of this stuff together. And so we reduce the noise quite a bit, and we end up with an 11.5 bit. Again, the trade-off comes from the trade-off is that we're going to get a cutoff frequency that's significantly lower than what the cutoff frequency of this direct front end is. Some of my very, very advanced customers that are doing robotics and higher, PhDs upon PhDs, ask us, hey, can you just turn this thing off completely and we'll do our own filter, because they want very specific trade-offs. That actually can be done, but in some of our parts, our MA732, but the 702 has a fixed filter with a fixed cutoff frequency. And so 11.5 bits of resolution. If you look up the MA702 data sheet, it says it's a 12-bit sensor in big headlines, and then it says, the 6 sigma resolution is 11.5 bits. All right, so let's talk about why this happens. We're going to go back. We've got our nice Gaussian noise diagram here that we used before, and I'm going to take a small filter window and scan it across that noise. When I scan it, what I'm doing is basically at the front edge of this filter, I'm going to output the average of all the points that are inside this window. So I scan, And at any given time, all the points that are inside that window are getting averaged. And I get an output that is something like this. It's actually, you would get, it's going to be a lot finer movements than this. I had to draw this in on PowerPoint, so I didn't do every micrometer, but you'll get something like this, where the output of the filter is significantly closer to the actual measurement of 0 than the full distribution. If I take a much larger window, this is, I don't know, 5 times larger, 4 times larger, and I do the exact same thing, scan it across, I'm going to get a much larger average, and that's going to, because I'm averaging more of these parts, more of these points that are close to the 0, my output stays very close to 0. So we should always use the big, large filter window, right? Because it's much better output. The problem is that, again, we've got this trade-off. So if I am now changing position or accelerating, and I told you guys before, our sensor has a state variable, a velocity state variable. Let's assume there's no velocity state variable, or you could change the word position to velocity in here. But in any case, as I scan this with that same window, the problem is I am averaging everything in that window. And so I'm going to get a little bit of a lag as this thing starts to accelerate, because when I'm here, I'm also averaging this point and this point and this point. And so I get this lag. With a large filter window, do the same thing, scan it across. And now here, I'm averaging this entire thing. So the output's going to be somewhere down here. And I get quite a large lag, especially the faster I accelerate, the more of a lag I get because of that large filter window. So there's a very intuitive, hopefully, or a very visual explanation of why that filter window size increases resolution but decreases the bandwidth. And why does bandwidth matter? Well, because you've got in a control system, oh man, we're into some fun stuff now. We're in the S domain, the Laplace domain. You've got a time constant. Our time constant for our position sensor is here. Our transfer function is here. And that time constant is completely linear with the cutoff frequency. So we could be talking in terms of cutoff frequency or just tau time constant. And for stability, this is pretty conservative. We want the sensor time constant to be 10 times smaller than the PID time constant. You could probably get away with 5 times. But this is a rule of thumb without going into a whole bunch of really rigorous mathematics. We'll say 5 to 10 times smaller than the PID time constant. If you get below that, you're going to start to see your system get unstable. And if you even get close to it, you're going to start to see that your PI system will take a long time to converge. So the faster you are here compared to your loop constant, the faster things will converge and the less overshoot and noise you'll get on your control system. All right. So let's take a look at, we showed the 702. The 732 is the same part that has a programmable filter. And so I mentioned that's an older part, and we'll compare that to one of our newer parts, the MA600, and there's a difference here. This is a Hall-based part, and this is a TMR, a tunneling magnetoresistive part. And so because of the TMR technology, which is just intrinsically faster and lower noise, we can push this entire curve over. This is a log scale on the frequency side. And so this looks linear. Remember, I mentioned it's every half bit of resolution, you have the cutoff frequency. So on a log scale, that makes a nice linear output. The MA600, everything's pushed over to the right. We gain 3 bits for the same cutoff frequency, so that's awesome. But this is not quite as linear, and you see it starts to drop off to a point where there's a limit here. It would be so nice if we could get this same linear, or at least log linear line to just go on, and we could say, oh man, we could get 16, 17 bits. I'm not going to go into it in detail here, but TMR has, whereas this is all pure Gaussian noise, TMR has a mix of Gaussian and pink noise, so 1/f noise, and that's why you end up eventually kind of saturating out. All right, so let's now take a look at data sheets, because we want to know. The important thing is we want to be able to generate this graph. We want to see this graph. What is the trade-off between our bandwidth and our resolution? Can we find a place on here to live? Do we need to go to the next generation part and find a place on here to live that our system will tolerate? Unfortunately, when we look at data sheets, sometimes it's very unclear, again, especially in magnetic sensors, what the actual resolution of a part is. So this is a competitor data sheet. They give the angle noise. So that's nice. That's good that they at least give the angle noise. Most data sheets, they will give the actual noise, the RMS noise. But these guys claim to have a 15-bit resolution. Pretty nice. 15 bits is significant, especially if you've got a relatively fast bandwidth. But 15 bits means that you would have a 0.01 degree noise resolution, right? Log 2 of 360 over 0.01 is 15.1. That is not the real resolution. That's the digital grid. That's the A to D resolution only. The sensor resolution is shown when we actually see the angle noise. Log 2 of 360 over 0.05 is actually only 10.2 bits, not 15. So I think some companies kind of either purposely or inadvertently take advantage of the fact that when you're comparing sensors, you just say, well, I need a 15-bit sensor. Oh, it says 15 bits. Cool. 15-bit sensor. You want to make sure that you take the time to find the noise. Sometimes you have to convert it into angle. As here, it's actually, they did angle noise, but not always. Make sure you convert it into the actual angle noise. Make sure you're looking at peak-to-peak noise. And then perform this calculation, the log base 2 of 360 over that noise. And we see that the sensor resolution is 10.2 bits. If you needed a 15-bit sensor for this application, this will not work. And you won't find out until you've built your system and it's unstable and you're saying, man, what's going on here? We've got another competitor. They give the ADC resolution. Now here they say, hey, this is the ADC resolution. And they have 3 modes. So they have 3 filter windows, slow, medium, and fast. And I say we're 15 bits, it's at slow mode, medium and fast, we're at 14 bits. Well, let's check that against the peak-to-peak noise. So for their slow mode, they're at 0.03, and I'm going to give them the benefit of looking at their typical value instead of their max value. They're at 0.03, and at their fast mode, they're at 0.1. If we perform this calculation, log 2 360 degrees over 0.03, we find out the resolution is 13.6 bits, not 15. In fast mode, which is of course even lower resolution because it's 0.1 degrees of noise, is only 11.8 bits, not 14. So you'd have to do the diligence of running these calculations. We put our resolution in and we say, hey, it's plus minus 3 sigma deviation of noise. We calculate our resolution based on our RMS noise. And you can see it's min and max because we have our filter, different ways that you can set your filter window. But if you were to run this calculation, log to 360 divided by 0.002, you get 14.5 bits. And if you run the calculation, log base 2 360 divided by 0.02, which is the maximum noise, you get the minimum resolution of 11.5 bits. So it's because we are so particular about how we define our resolution, we make sure that we put that on the data sheet. You can find this, by the way, in our NMA 600 data sheet, the various filter windows. You find this table that says, okay, hey, we've got all these filter windows. And you can exactly see the trade-off then. And it pretty much follows what I said. For 12 and a half, for a half bit of resolution, so from going to 12 to 12 and a half, the cutoff frequency is halved. A little more actually than halved. And again, that's because this is that TMR part that doesn't have exactly log linear output, but the general shape holds true. And then you can actually see the cutoff frequency at various frequencies. Okay, so last thing I guess I want to mention, I mentioned this at the beginning, but I was looking for a place to put this slide, is why use a magnetic encoder anyways, when you could just use an optical encoder? And you can find an optical encoder that's, heck, you could find an optical encoder that's 20 bits. So then why go through all this mathematics and looking at graphs and the trade-offs between bandwidth and resolution when you could just throw an optical encoder on? And there's two main reasons. One is size, and the optical encoders, they're large. You have a code wheel, a disk, you have the photo transistors. For a small brushless DC motor, the encoder can be the same size as the motor. Whereas if I was to take this motor and use a magnet, I would just throw a magnet on the end of this shaft, throw a PCB, which is, whatever it is, the thickness of a PCB right here, and our sensor would sit off to the side. So it's a space and especially a cost savings. This magnet maybe costs, I don't know, 3 cents, 2 cents. The IC here at volume, you're talking around $1, $1.50, compared to this thing that is going to be anywhere from $4 or $5 up to, well, if you want IP, ingress protection, so you don't get dust and dirt in there clogging up your code wheel disk, this thing can literally go up to hundreds of dollars. So the point is, this takes less math, but we're engineers. Let's take 20 minutes up front, do the math, do the calculations, figure out where we need to live, and save a lot of costs and a lot of space. Yeah, and then just to summarize, I showed this graph before. This is our old Gen 1, our MA732 or MA330 part. Our TMR Gen 2 parts are a significant increase. The entire graph is moved up and to the right. So for the same bandwidth, you get a much higher resolution. For the same resolution, you get a much higher bandwidth. 0.5 degrees of INL over the entire operating temperature, which you could get down to 0.1 with some calibration, up to 14.5 bits. And again, that's plus minus 3 sigma. No latency because of our latency compensation. And this thing is easy. It's flexible. You can put it end of shaft. You can put it side shaft. You can even put it side shaft orthogonal, where you would flip this 90 degrees. And I'll even put a plug-in for myself personally. Comes with the best support in the industry. You have a motor, or you have a mechanical design, you can send me anything from a napkin drawing to a CAD file, and we'll iterate back and forth. And I'll say, hey, I can help you design the magnet. I can help you design the mechanics. I can help you design the electronics. That's the fun part of my job, by the way. I'm happy to do that. And so we'll support you through your entire design process and make sure that you get, and that you even live on the correct place in this curve based on the criteria of your feedback system. That's all for me, but I'm happy to take questions. It looks like we already have one.
Great, thanks, Ted. As we mentioned, we do have one question in there. For those of you that may have joined late, if you mouse over your Zoom webinar interface, you'll see the QA button. Click on that, type away, and we'll make sure to answer the question. The number one question we always get, for those of you that may have gotten here a little bit late today, is this presentation going to be available? And yes, we record the session, we send out the presentation. So you'll look for that in the next couple of days. And remember that you can always go to monolithicpower.com/webinars to see that. So
Yeah.
with that, let's get to the first question.
Sure. It looks like somebody's asking, they want a very simplified, a kind of single word answer for what is resolution and what is bandwidth. Because the explanation I gave was complex. I agree. The explanation I gave was complex. The idea is to show that it's not as simple as what it looks on the surface. But let's look at the surface. Let's take a surface answer. Resolution is simply the smallest difference that you can detect. We're talking about an angle sensor, and I say I have a resolution, and we'll put it in degrees to make it simple. If I say I have a resolution of 5 degrees, it means that if I change a rotating knob only 2 degrees, I don't see any difference in my output. Not until I've rotated it at least 5 degrees will I see an change in my output. For our parts, typical resolutions are let's say a 12-bit resolution. I think if I'm doing my math in my head correctly, it's about 0.008 degrees. So it means that if I were to turn a knob or a motor less than 0.008 degrees, I'm not going to see a difference in the output. And even if I do, I can't be sure if that's noise or if that's an actual physical change in the angle. So that's the hopefully simpler explanation of resolution. Bandwidth is simply if I were to take a motor and not rotate it at a specific frequency, but vibrate it back and forth at a given frequency. In other words, accelerate to a max speed going clockwise, slow down, accelerate to a max speed going counterclockwise, and do that. So I have this sine wave of position. What frequency would I get to where I wouldn't, the output of my sensor would stop showing that there's any type of oscillation and just assume that it's in a single position? That's in a word dynamic bandwidth. It gets more complex than that, of course, but those are, hopefully that's a simple explanation that works. All right. Can you give me a hint on how to determine latency? Yeah, that should be a main specification in any data sheet for any sensor. Should be latency, and it's will range anywhere from I think our MA732, our last our previous generation parts have about a 6 to 8 microsecond latency. I typically see competitors with tens of microseconds of latency. You almost never see a sensor, at least a magnetic angle sensor, with milliseconds of latency unless they're really, really straining their filter. But it should be right there in the data sheet. Latency should be right there in the data sheet. We say that our MA600 has 0 latency, but that's because the filter itself has latency compensation. So it shows, I think it's one of the highlights. We say, hey, zero latency. And I'm pretty sure on all of our data sheets, the NPS data sheets, it's in the, the bullet points, the kind of marketing bullet points, what the actual latency is. And it's pretty common. I've not found a sensor where it's not somewhere in the data sheet. So you should be able to find it in the data sheet for sure. Are there any supply chain delays with this new part? Everybody knows the semiconductor industry right now is pretty crazy. Lead times are crazy. I don't have any supply chain delays. So in general, it takes us from the time that we get a demand, and we're talking about millions of pieces, from the time that I actually see a demand or a PO. It takes, if I don't have enough in stock and I have to actually start wafers and get things going, we're talking about 5 months is the minimum. Let's say I get a huge order and I say, oh, wow, I got to start wafers and get them in process. Usually we've already got wafers in process, but again, I'm assuming worst case scenario, we're talking about 5 months. For orders that are in the thousands, tens of thousands, hundreds of thousands, we almost always have some parts available and some parts that we can shift around. So there's no easy answer for it. It's case by case, but the absolute maximum is 5 months. So yeah, that's where we're at today. I think we're starting to see the slowdown, and so I think that's going to continue to get better and better. The standard lead times are going to start getting better and better because we're starting to see. Yeah, we could turn this into a whole semiconductor market discussion. I think that's a different webinar, but yeah, we're starting to see it slow down. Typical power requirements of a magnetic sensor. So if it's on all day, in other words, if you don't turn it off, you're looking at around 8 to 12 milliamps of sync at 3.3 volts. We do have some 5-volt parts. Most customers use 3.3. So 3.3 times 12 milliamps, whatever that is in 36 milliwatts, something like that. So not huge power. We do have parts that are designed specifically for running off a battery. That would be our MA780 series. And it has its own go to sleep mode, and then it'll just wake up periodically to check the angle and say, oh, it's still the same. The typical application for that's like a thermostat or a door lock that sits there most of the day not doing anything. But once it starts to turn, once someone starts to turn something, it wants to wake up the whole system and say, hey, let's go. It's time to do stuff. That will sit there, and it's very dependent on resolution and how often you want to check for the angle. And the reason it's dependent on resolution is that if that filter window is large, you have to wake up for a longer time to make sure you get to through the entire filter window. But a typical for that is microamps. So that will sit there and only consume microamps until it sees something happening and your system wakes up and it says, okay, hey, let's go full speed, and then it goes up to 8 milliamps. But yeah, that's the typical power requirements. How does the readout time delay relate to error or bandwidth? So the delay is the readout time delay is basically a function of latency. And then during acceleration, so not if it's sitting still or at a constant velocity, during acceleration, bandwidth will affect an even further delay. So you have your latency times speed is going to give you your angle lag. And again, the MA600, because it's got compensation, there won't be any. But if you have a low bandwidth and you start to accelerate, you can calculate that acceleration. Oh boy, let's see if I get this right. It is acceleration times tau squared. So we showed that there's let's see if I have it on here. Yeah, so you can see there's a tau associated with every cutoff frequency. That tau is in microseconds. So whatever you've set your filter to, let's say we've set it to, it's at the default of 5, so 40 microseconds. Based on your acceleration in radians per second squared or degrees per second squared, you can multiply that acceleration times 40 microseconds squared, and you'll get the angle lag in degrees or in radians. How latencies are curve. Sorry, how resolution and bandwidth you showed on PowerPoint x-axis and y-axis. Basanth, I'll come back to you because I'm gonna have to get clarification on that question. So let me come back to that one. What interface between sensor and MCU is best for low latency, and which one is best for higher resolution? SPI. SPI is best for low latency and high resolution. You can run it at 20 megahertz, no problem. We have various outputs, but if you want fast and full resolution, SPI. Is linearization possible in every position of the sensor in side shaft configuration? Yes, it absolutely is. In side shaft configuration, we have 2 different ways that we linearize. One is we have a so-called bias current trimming. This is something I can get into in depth if you email me. By the way, I should probably put my email up here, and I'm just going to do that. I'm going to try to edit this real quick and throw my email up here. I don't know if it'll work. Give me 1 second while I answer this question. Multitasking is not my best, but we'll see what we can do here. Do you want to keep implementation discard? Oh crap. Yeah, I probably screwed this up. Anyways, hey, I think I did it. To answer your question in a very basic way, and then you can email me and I can give you a more in-depth answer. And we want to move that down a little bit. And I think if I present, hopefully you guys can see my email address. Go ahead and jot that down and you can email me for more in-depth questions here. So anyways, BCT, bias current trimming, it works by when you're in side shaft position, and Kelly, watch me on time if I'm going over or whatever. I need to speed things up. You tell me. I think we still have 7 minutes. We can correct the ellipticity of the field. So when we're in side shaft, the field doesn't look like a circle. It looks like an ellipse. And we have an internal correction mechanism that we can put in place that basically de-eccentrises it, takes all the eccentricity out so that the field looks like a circle again. That kind of relinearizes the output, so to speak. That does not take away all the intrinsic INL. And so then the second step for that is to actually do an in-system calibration. And that'll take us from the 0.5 degree intrinsic INL down to 0.1 because we're in situ and all we have to worry about then is temperature drift. But that can be done in any position of the sensor. That can be done whether it's on axis, off axis orthogonal. Yes. Okay, for MA600 sensor in pre-data sheet, it is given the AVDD and DVDD decoupling capacitors are prescribed to be 10 millimeter radius away from the center of the sensor. I see this cost a bit of space. Will it make a big difference in the sensor measurement if the decoupling capacitors are within 2 to 3 millimeters? This is something I saw this for the first time about a week ago. I had another customer that said something to me about this, and I don't know why we said that. It seems like those capacitors, I've never ever had a problem with a decoupling cap deflecting the field. And so I think a designer that maybe it was a relatively new designer put that in there, this 10 millimeter radius. To me, it's, yeah, I'm with you. Most customers don't have the board space for that. I will say I've never ever seen a problem with decoupling caps being, basically right on top of the sensor. In our eval kits, the decoupling caps are right on top of the sensor. I am going to find out why or how that got in there, and get that corrected. Because yeah, I know that's a big chunk of real estate. If for some reason it wasn't just a new designer or somebody who was following like a super conservative best practice that they got from somewhere else, I'll specifically, I've got your email address, Mohammed, I think in the registration, and I'll email you and say, hey, actually there's a real reason for this. I'm 99% sure that this was just being way over conservative, but I'll let you know. What is the smallest footprint housing? The smallest footprint for the MA600 is 3 by 3 millimeter QFN, so 3 by 3 by 1. The MA782 we have in a 2 by 2 by 0.6 millimeter package. So these are pretty tiny parts. Thanks. Oh, thank you, Jonathan. Does the mounting position coaxial beside the axis affect the angular precision? No, ideally not. It's because we have this so-called BCT correction. It should not affect the angular precision. Now, what I'll tell you is that when you're on axis, mechanical tolerance stack up affects. So you're never perfect, or at least, we're all electrical engineers, so we can make fun of the MEs that always want some tolerance. Or maybe there's some mechanical engineers on here, then I can't make fun of anybody. But in any case, I've never met a mechanical engineer who says, yeah, I can get you right on this spot with plus minus 0 millimeters of tolerance or tolerance stack up. In the real world, there's always some tolerance. So when you are on axis, if you're off by, let's say, a 0.5 millimeter or 0.2 millimeters, that has some effect on INL. That was one of the things that we talked about at the very beginning of the presentation, that intrinsic magnetic misalignment. The effect of magnetic misalignment in angle, in degrees, is significantly less for the same amount of stack up when you're on axis. So when you're off axis, if you have that stack up, it will cause a higher error than if you were on axis. Usually 0.3 degrees accounts for an off axis typical, for as much as you can say typical tolerance stack up. Let's see here. So I've got Vasant. Okay, so resolution bandwidth you showed in your PPT X and Y. Yeah, so Vasant, I don't know if we can unmute Vasant for a second. I'm not sure. I don't fully understand this question. It said resolution and bandwidth you showed in PPT X axis and Y axis. Can you give me a little more detail on that, Vasant?
And I believe I've hit the control to allow you to, there you go. Okay, now he should be able to talk.
Cool.
Vasant, go ahead.
Oh, is he still there?
He's still there. I'm not showing him as muted any longer, so, but might not have had a good audio.
Okay, no worries. Vasant, you can always email me too if you're having trouble with your audio. You can email me and I'll make sure to answer your question in detail. And then Vasant asked another question. And this one I do understand. He says, can we use rotor magnet to sense position instead of external magnet? Will it affect resolution and bandwidth? What Vasant is asking is, in a motor, can we use the actual rotor magnet as opposed to a separate external target magnet? The answer is yes. Again, we don't get anything for free. We got rid of a magnet and we don't get anything for free. So here's the trade-off. You can use the rotor magnet. And in fact, I'm working right now very diligently with a bunch of tool companies to try to replace all the UVW discrete Hall cells that they used to commutate their motors with a low-cost mag alpha, sensing the rotor magnet directly. Here's what you lose and here's what you gain. The gain is simple. You get rid of a target magnet and save a bunch of space, and you don't have to worry about how you're going to attach a target magnet. What you lose is the ability for true absolute mechanical position. A rotor magnet is always going to be, I mean, theoretically, you could have a dipole rotor magnet, but in practice, it never happens. It's always at least 2 pole pairs. And so let's say we have a 2 pole pair rotor magnet. I don't know which half of the circle I'm looking at any given time. So for every mechanical rotation, my sensor is going to see 2 magnetic rotations. And because of that, I lose the ability for true absolute mechanical output. Now, if you're just trying to commutate the motor, it doesn't matter. No one cares what the mechanical is. You only care about the electrical. And so for stuff like block commutation, it actually works really, really well. And yeah, you can do that. The only other issue is that rotor magnets are designed for usually max efficiency, max torque, and not so much for a real nice sinusoidal field. And so sometimes you get a little bit ugly field and you have to do either some calibration or just live with a little extra sloppiness. To give you an idea, a typical INL on a sloppy, like, think of a tool motor, which typically doesn't have a nice sinusoidally magnetized magnet. It's got like bar magnets in laminated steel. I'm looking at like plus minus 6 degrees. Again, for block commutation, no big deal. It doesn't matter. If I use a target magnet, I can get a real nice, either a dipole or if I'm using multi-pole magnet, I can get real nice sinusoidal transitions. It does not affect resolution, with one caveat, and I'll get to that. And it does not affect bandwidth at all. Resolution is affected in the sense that the lower the magnetic field, the more resolution, the less resolution you get at the same filter window, the same bandwidth. It's a small effect. It's a relatively small effect. There's not a lot of difference between, let's say, 100 millitesla and 30 millitesla. So it's not a huge effect. But in general, when you're using a rotor magnet, because it's not designed, the flux is designed to be trapped in the air gap, you get a lower magnetic field, so slightly less resolution. There's a long answer to a relatively short question. And then I think that looks like all the questions. Oh, let's see, Klaus.
One more pop. Did you address, he had typed in while you were answering, Ted, about, I guess he was just thanking for the clarity.
Yeah, just said
never mind.
Yep,
okay.
No problem. Yep. Thank you, Vasant.
Yeah, and I can actually answer a question here.
Yeah, so that's right. Yeah.
monolithicpower.com/webinars. You will see all of our past presentations available on demand. And we will email out to you, everyone that's registered, links to the presentation and to the video, so that you'll be able to review this all again. All right.
Well, thanks, guys. Appreciate everybody sticking around for the whole thing. And again, feel free to email me if any questions come up. And enjoy the rest of your morning, day, evening.
Thanks, everyone. Have a good day.